Recurrence relations are actually three types. One is homogeneous, another one is non-homogeneous, and a linear and non-linear. In our syllabus, we are discussing the only linear recurrence relations. In the linear recurrence relations, there are two types. One is homogeneous, another one is the non-homogeneous. Our today's class is non-homogeneous recurrence relations. Non-homogeneous recurrence relations. Non-homogeneous linear recurrence relation. This is our today's topic. Non-homogeneous linear recurrence relation. First of all, I will explain what is this non-homogeneous linear recurrence relation. Please suppose, for example, general form of non-homogeneous linear recurrence relation. Now onwards, I will write simply non-homogeneous linear recurrence relation. What is the general form of the non-homogeneous recurrence relation? Suppose, for example, if you write a recurrence relation such that an plus, the previous class already I told to you. Anyone can tell, just remember to me, or please tell me what is the general form of the recurrence relation? Yes. Now check it. See, my dear students, are you able to see the screen?
Yes, sir.
Yeah, why are you not telling? I asked to you, but no one respond. That's why I am continuing the class. Okay, once again I will repeat. Clearly look at the board, all of you. See, non-homogeneous linear recurrence relation. Simply I will write non-HLRR, non-homogeneous linear recurrence relation. The point number one, what is the general form of the non-homogeneous linear recurrence relation? This general form is A naught, C naught an plus C1 an minus 1 plus C2 an minus 2 plus and so on to plus Ck an minus k equals to Gn. What is this Gn? Gn is the function of n or function in terms of n not containing any a term. That is a very important. Here what is the important thing is, here this right side function, this right side Gn function, clearly listen my dear students, this is the very important. The right side function means this Gn does not contain a terms. Keep this point. Only all the, that means we have to write all the a terms, all the terms which contains a, that all terms we have to write in the left side. We can write only the function which contains the only n terms. That means Gn is the function of n. That means this right side part contains either constant or a function in terms of n only. Okay, it does not contains any a terms. This is the very important. This is okay. That means in the starting step one, we have to write all the a terms in the left side. Keep the remaining terms, either constants or n terms, in the right side. That is called the general form of the non-homogeneous linear recurrence relation. Now, what is the solution of the general? What is the general solution? What is the general solution or simply solution? of the non-homogeneous recurrence relation. The non-homogeneous recurrence relation solution contains the two parts. First part is said to be solution of the homogeneous recurrence relation or corresponding homogeneous recurrence relation. The second part is said to be particular solution. That means we have to find the two solutions. One is for homogeneous recurrence relation, another is particular solution. So the combination, the sum of these solutions is said to be general solution. But how to find these two solutions? Come to the first point number 3. So here the first one is homogeneous. Here the first part is homogeneous linear recurrence relation. How to find the homogeneous? Homogeneous means in the equation 1 gn equals to 0. Suppose this gn equals to 0, then the equation 1 can be converted into homogeneous linear recurrence relation, then it is denoted by 2. That means in the equation 1 I am taking gn equals to 0, then the remaining equation is a0 an plus c1 an minus 1, c0 an plus c1 an minus 1 plus c2 an minus 2 plus and so on, ck an minus k equals to 0. Equals to 0 means gn we are taking 0. So gn is 0, then it is called homogeneous linear recurrence relation. This is the equation 2. So in the solution, the first part is solution of homogeneous linear recurrence relation. The equation 2 is the HLRR, homogeneous linear recurrence relation. Now we require the solution of this one. How to find the solution? I clearly explained in the previous class. What I told to you, first you can take substitute an equals to r power n and an minus 1 equals to r power n minus 2, an minus 2 r minus 2 and plus and so on, an minus k. At the place of an minus k, we can replace r power k minus r power n minus k equals to 0. After that, what I told to you, you can take the least power. What is the least power here? Least exponent is n minus k. You can take n minus k common. R power n minus k is common. Then the remaining is c0 r power k plus c1 r power k minus 1 plus c2 r power k minus 2. Similarly, if you write, finally you will get here some ck minus 1 r plus ck equals to 0. Therefore, finally, this can be written as c0 r power k plus c1 r power k minus 1 plus c2 r power k minus 2 plus and so on, ck minus 1 r plus ck equals to 0. This is called the characteristic equation. In the many examples we solved on this one. This is the third one. This is called the characteristic equation. This is characteristic equation. I clearly told to you. This is the characteristic equation. After finding the characteristic, after getting the characteristic equation, the step 5 is find the roots. Find roots. That roots contain denoted by r1, r2 up to here the highest exponent is k. Therefore, you will get the k roots. After getting the k roots, how general solution already you know. Already know the solution of homogeneous linear recurrence relation. I told to you 3 cases here. Here I told the 3 cases. Already you know the 3 cases. Okay. Suppose all are the distant real roots. The next one, repeated real roots. And the third case is, what is the third case? Students, already I told you the 3 cases. What is the third case?
Roots are irregular.
Very good. Roots are distant. Sorry, roots are, what is the third case I told? Complex numbers. Am I right? Yes or no? Complex numbers. The third case is complex numbers. Then by using these 3 cases, already we discussed. By using these 3 cases, we can find the general solution AN of H. This is the step 4. How to find this one? I explained in the class. So this is over. Now come to the particular solution. Okay, the seventh step is the particular solution. This is the very important, my dear students. Okay, the seventh step is particular solution. Particular solution. First 6 steps already we completed in the class. Particular solution of non-homogeneous linear recurrence relation. Non-homogeneous. Clearly listen. Non-homogeneous linear recurrence relation. This particular solution is denoted by AN of P. So how to find this one? Here there are 3 cases. This is the very important. Here there are 3 cases. The case 1. It is the very important, my dear students. Everyone should remember these 3 cases. Suppose GN. GN already I told to you. Suppose GN is a constant. The point number 1. What is the right side part? Gn is suppose some constant C1 constant. At the time we have to take the AN of P, which is equals to here also some constant D. Suppose the constant D is not satisfied, immediately you can take N into Dn. Dn. Suppose Dn is not satisfied, then you can take Dn square. Then Dn cube. Similarly, we have to test. This is the case 1. Once again, I am telling you, suppose the Gn means the right side part. You can see in the equation 1. All of you see the equation 1? In the step 1, the equation 1, Gn is already here. The right side part, there is a function. There is a one function in terms of n Gn. Suppose this Gn is constant. The right side part is constant. At the time, the particular solution AN of P is either constant. First we can take constant. If it satisfies the equation, okay. Otherwise you can take Dn. Otherwise you can take Dn. Suppose Dn satisfies the given recurrence relation, okay. Otherwise you can take Dn square. Otherwise Dn cube. Similarly you can find it. That is the case 1. The second case is suppose the Gn is constant power some n, some value n, constant power n. Suppose constant power n, then how can we denote this one? Here also you can take the particular solution AN of P equals to, when it is a constant power n, you can take D into that constant power n. Suppose D into constant power n satisfies the equation, okay. Otherwise in that case, immediately you can take Dn into C power n. Suppose this condition satisfies the equation, okay. Otherwise you can take Dn square into the constant power n. Otherwise similarly same Dn cube into constant power n. This is the case 2. And the third one is linear. This is the linear case. What is this linear case? Suppose the Gn is in the form of C0 plus C1 into n. This is called the linear case. In this case, you can take the particular solution AN of P equals to the D into, here C0 is there, you can take D0, then plus D1 into n. So these are the cases. These are the 3 important cases we have to discuss in this class. Okay, once again I am telling you, all of you listen. These are the 3 different cases. You will get the only one of the case in the problem. Keep this one. You will get the only one of the case in out of 3 cases. But you have to remember what is the right case here. That is very important. Suppose first we have to decide what is the Gn. What is the Gn in the problem? Suppose case 1, the Gn is the constant C. The Gn is the constant C. Immediately you can take AN of P equals to D. an of p equals to d. Suppose d satisfies the given recurrence relation, okay. Otherwise, you can take dn. Otherwise, dn does not satisfy the case, then immediately you can take dn square. After that, dn cube power. Suppose second case, gn equals to c power n. Then you can take an of p equals to d into c power n. Suppose d into c power n satisfies the given recurrence relation, okay. Otherwise, you can take d into n into c power n. If it satisfies, okay. Otherwise, d into n square into c power n. Similarly, you can write. Third case. What is the third case? Suppose gn equals to linear. Linear means c0 plus c1 into n. In this case, you can immediately take the particular solution an of p equals to d0 plus d1 into n. These are the three cases. Can you start the problems on this one? Students, can you start the problems? Yeah. So these three cases you have to remember. These are the very important, my dear students. Okay, in examination, they will ask one of the essay question, one of the model. You can get one problem on these three cases. Okay. Yeah. Now I will start the problem. All of you listen. Okay. Just a minute. Are you hearing properly? Yes. Okay. Okay. Come to the point. So after getting this is the step number 7. After getting the step 7, what is the step 8? Now come to the point, step number 8. So it contains 10 or 11 steps. Each step I am clearly telling you. If you just concentrate, then automatically you can easily understand. But you have to concentrate. After getting this an, substitute an of p. Substitute an of p in the equation 1, in the given non-homogeneous linear recurrence relation. That is we denoted that equation 1, and find the constants. Constant d's. What are the d's in the AP? You can see an of p contains the term constant d. Am I right? Are you seeing the constant d in the an of p? Yes or no? Hello? Yes. Yeah. This is the equation. You will get the one of the equation. That equation I am denoting by 5. Okay. Substitute an. An means 5. An means 5. So this equation 5 already written. One of the equation you will get in the table. That is denoted by 5. That 5, that equation an of p means the equation 5. We have to substitute in the given non-homogeneous linear recurrence relation. Then we can find the constants d's. So after that eliminate d in equation 1. Eliminate d in equation 5. Okay. Then after that here, this is the one of the important case. We will get general solution. General solution of non-homogeneous linear recurrence relation. Equation 1. So finally you will get the general solution here. But here there is a 9th step is also there. What is this 9th step? It is a very important, my dear students. What is this 9th step? 9th step means if there are initial conditions. initial conditions, if there are initial conditions, then we can eliminate constants in the general solution. In the general solution, suppose for example 6, we will get the general solution. This is I am denoting by 6. In the general solution 6, then finally, or hence we get final general solution. What are these steps? This is denoted by sum 7. Okay, all of you listen clearly. I used the many terms here. What are the terms? I will clearly explain. This is the sum equation 8. This is sum equation 7. 7 I will denote like this. This is sum equation 7. Yes, come to the point. This is sum equation 6. This is sum equation 6. Yeah. All of you once again listen. I will explain all the steps, and then I will solve the problems on these methods. This is the equation 1, step 1. This is the step 2. This is the step 3. This is the step 4. This is the step 5. Yes. For your understanding, I am writing these are all the steps. What are the steps I told to you? All of you listen. I will explain one by one. Look at step 1. First, the given equation write in the form of C0 an plus C1 an minus 1 plus C2 an minus 2 plus and so on to Ck an minus k equals to Gn. This is the equation 1. Equation 1 means write all a terms in the left side. Write all the a terms in the left side or an terms in the left side and remaining n terms and constants in the right side. The right side part is denoted by Gn. That is the step 1. Here I clearly written that Gn does not contains any a term. Gn does not contains any a term. Okay, that is the very important. Any a term. After that, general solution of non-homogeneous linear recurrence relation contains the two parts. The general solution an equals to an of h plus an of p. Here an of h is called solution of homogeneous linear recurrence relation. An of p is called the particular solution. How to find these two values? First come to the point homogeneous recurrence relation. If you require the homogeneous recurrence relation, first you can take the right side part should be identically 0. That means Gn equals to 0. Suppose Gn equals to 0 in the equation, the right side part same. I am writing the same equation. In this equation, the right side part is 0. Here the Gn is 0. Here the Gn value 0. Then it is called the homogeneous recurrence relation. It is denoted by 2. After that, already you know characteristic equation. Characteristic equation means at the place of an we have to substitute an minus 1. This is already you know. At the place of an you can substitute r power n, and at the place of an minus 2 you can substitute r power n minus 1. At n minus 2 you can substitute r power n minus 2. At an minus k you can substitute r power n minus k. If you substitute these are all the terms, then immediately you can take the least power. What is the least power here? Already you know, here the n minus k is the least exponent. This is the least. N minus k is the least exponent. Am I right? This is the least exponent. This least exponent is the common here. If you take r power n minus k common, then you will get the characteristic equation. It is denoted by 3. Okay. 3 is the characteristic equation. After getting the characteristic equation, already you know we have to find the roots. So roots already how to calculate the roots already you know in the yesterday's class already we discussed. After getting the root, how to find the solution of homogeneous linear recurrence relation, I told the three cases. One is the roots are distant, the roots are equal, repeated roots. Then we can get an of h. This is the equation 4. Okay, we solved the many problems in the class. Already I solved the problems on the blackboard or whiteboard also. So you can understand this one. Now come to the particular solution. When we will come to the particular solution, the particular here the particular solution contains the many cases, but in our examination there are the three important cases are there. One is Gn equals to constant. Another one is Gn equals to constant power n. Third one Gn equals to C0 plus C1 into n. So these three cases are very important for our examination. Here the first case, suppose A and P. A and P means here Gn is constant. Immediately you can take the particular solution equals to D. Suppose D satisfies the given condition, then okay. Suppose D does not satisfy the given condition, at that case you can take immediately D into n. Suppose D into n satisfies the given recurrence relation, okay. Otherwise you can take D into n square. D into n square satisfies the recurrence relation, okay. Otherwise you can take D into n cube. So these are the cases. Similarly, the next one, suppose the general Gn is C power n. In that case, first you can take D into C power n. This is the case, first one. First you can take D into C power n. Suppose D into C power 1 satisfies the equation, okay. Otherwise you can come D into n into C power n. If it satisfies, okay. Otherwise you can take D into n square into C power n. Similarly, D into n cube into C power n. These are the other cases. First, we can start our journey from D into C power n. Come to the linear. Linear means C0 plus C1 into n. This is called the linear equation. So you can take an. In this case, the particular solution is D0 plus D1n. These are the three cases. These you will get the one of the case in the problem. That is denoted by equation 5. Equation 5 is the particular solution. So in this particular solution, what can we do in the step 8? In the step 8, substitute this an of p. An of p means equation 5. This equation 5 substitute in the given non-homogeneous recurrence relation. That means in the equation 1 and constants. Constants means d's. The constants means the d's we can eliminate. We can eliminate the constant d's. So if you eliminate the d's, then we will get our required general solution of the non-homogeneous recurrence relation. In case the last 9th step, if there are initial conditions, then we can eliminate the constants in the general solution of 6. General solution of 6. The general solution of 6 already I told you, this is the equation 6. General solution of 6. Then we will get the final general solution, that is the equation 7. These are the steps. These are the steps I will explain by the example. Everyone should concentrate. It is very, very easy to you. Okay. Now I am going to follow the sum of the problems. Yes. Now all of you concentrate, my dear students. Concentrate, my dear students. Don't deviate. Can I start the problems? Hello.
Yes.
Are you hear me proper? Yeah. Okay. Good. See the first one. Case 1. First, I will start the case 1 problem. Case 1. This is belongs to the first case. First case means constant. Solve the recurrence relation. Follow the recurrence relation. Follow the recurrence relation. What is the recurrence relation? An minus 2 into an minus 1. 2 into an minus 2 into an minus 1. That equals to 2 minus an minus 2. With a naught equals to 25, comma a1 equals to 16. This is the given problem. Here in the last case I told to you initial conditions. Here these are called the initial conditions. See here in the finally they given these are called the initial conditions. Initial conditions. Okay. So this is the 5th step in the procedure. See if there are initial conditions, then we can eliminate the constants in the general solution 6. Okay, this is the last case. In case if there are initial conditions, a naught equals to 25, a1 equals to 6, these are called the initial conditions. That means in the procedure we have to solve this ninth step also. That is okay. Come to the point. See, I will explain the only procedure. What is the first one? General form of the non-homogeneous linear recurrence relation. General form of the non-homogeneous recurrence relation means we have to write all the a terms in the left side and keep the only n terms and constants in the right side. Don't, here I clearly written, does not contain any a terms. Any a term, this is the a terms, any a terms in the right side. That is, so that's why according to that one step solution. In the solution, I clearly told to you, my dear students, what are the steps involved here. In the solution, what is the first step I told to you? The first step is write all the a terms in the left side. See, an is already in the left side. Okay, good. Minus 2 into an minus 1 is also in the left side. Good. But see here, minus an minus 2. Here, minus an minus 2 in the right side. That's why this minus an minus 2 we have to write in the left side only. This minus term comes to this side, it should be plus. Equals to constant. Just observe here, all the a terms in a particular order and also all the a terms in the left side, only constants in the right side. So this constant, what is the constant here? This right side part is denoted by gn. This is called the an. That means simply an or c0 an plus c1 an minus 1 plus c2 an minus 2. This is the general form. So here gn means this is the equation 1. Now come to the step 2. What is the step 2? I clearly told to you. See, step 1 is the general solution. I clearly told to you this is the equation 1. Step 2 means the general solution of non-homogeneous recurrence relation contains the two parts, sum of the two parts. I will write that one. Yes, general solution of non-homogeneous non-linear recurrence relation. Non-homogeneous linear recurrence relation 1. General solution of non-homogeneous recurrence relation 1. An contains the two parts. One is an of h. This is the homogeneous solution for homogeneous linear recurrence relation. Another one is the particular solution. This is the equation 2. Now we require, now come to the third one. What is the third step I told to you? If the right side part gn equals to 0, if you require the homogeneous, this is the homogeneous, this is the solution of homogeneous linear recurrence relation. If you require the homogeneous, the general gn must be 0. Suppose gn equals to 0, then what happened? The remaining just listen clearly. Gn equals to 0 in the equation 1. In the equation 1, the gn equals to 0, then what happened remaining? The remaining is an minus 2 into an minus 1 plus an minus 2, which is equals to 0. This is the equation 3. It is called homogeneous linear recurrence relation. This is a homogeneous linear recurrence relation. So now we require the solution of this one. Now come to the step 4. What is the step 4? Step 4 is characteristic equation. Characteristic equation of 3. How to find the characteristic equation? I told to you. At the place of n, you can substitute r power n. At the place of r power n minus 1 is replaced by n minus 1. And a n minus 2 replaced by r power n minus 2 equals to 0. Here n minus 2 is the least one. That's why you can take n minus 2 is common. If you take n minus 2 common, you will get r square minus 2r plus 1 equals to 0. Finally, this can be written as r square minus 2r plus 1 equals to 0. This is the characteristic equation. Characteristic equation of 3. Therefore, here you can easily understand this is a square minus 2ab plus b square. A square minus 2ab plus b square formula. Therefore, a square minus 2ab plus b square means a minus b whole square formula. A minus b whole square formula means r minus 2 equals to 0. 2 times we can get. Therefore, here the roots are equals to 2 comma 2. Therefore, there are two roots. The root is repeated here. Therefore, finally what happened? Roots.
Sir, 1,1.
Oh, sorry. Thank you very much. Thank you very much. These are, yes. Yeah, thank you. R minus 1 whole square. Thank you. Here, r minus 1 whole square equals to 0. R minus 1 whole square equals to 0 means r equals to 1 comma 1. Therefore, finally, roots are r equals to 2 comma 2. Roots are repeated here. You can see what I told. Fourth one is characteristic equation. Characteristic equation already find. Fifth one, what I told. Fifth one is the roots. R1, R2, R2 up to Rk. Here there are two roots. The roots are repeated. Here there are three cases. Solution of the homogeneous linear recurrence relation contains the three cases. One is distant root. The second one is a repeated root. Here the root is repeated 2 times. Here the root is repeated 2 times. Here this is the step 5. Step 5. So here the root is repeated. So repeated. Root is repeated. If the root is repeated, this is the second case already we discussed. General solution. Anyone please tell me what is the general solution? What is the general solution here? The general solution is denoted by an of h. What is the general solution? Root is repeated, therefore the general solution. Tell me.
D1 plus
Yeah, tell me D1 or C1. Yeah.
and NC2
Yes, very good.
into R power
Very good. Into R power
R1
n.
power n.
This is, yeah, R1 means here what is the R1? Yeah, R1 power 1. Okay. Finally, this can be written as C1 plus NC2 into R1. What is the R1 means? Our root. Root is 1. Yes or no?
Yes.
Yeah. Finally, our answer is C1 plus N into C2. This is the equation. Next equation. An of H. This is the our required general solution. Here the required general solution is okay. Now, after getting the general solution, you can see the board, all of you. You can see the all of you in the step 6, solution of homogeneous linear recurrence relation. An of H, the equation 4 is already we calculated. Now come to the next one. Particular solution. Step 6 is particular solution. Here Gn equals to, in the given problem, the C is constant. Gn equals to 2. So for Gn equals to 2, what I told to you, An of P equals to, first we have to take a constant D. First we can take a constant D. Therefore, here, this is equation 4. Okay, this is the general solution. Next, come to the step 6 or 7. 7. What is this? Particular solution. Particular solution is depend upon the Gn. Particular solution is depend upon the Gn. Here Gn equals to, in the given problem, Gn equals to constant 2. Check it. See here in the given problem, you can easily observe here the Gn equals to 2. Am I right? Yes or no?
Yes.
Yeah. If Gn equals to 2 means, you can see here Gn equals to C. C means constant. If Gn equals to C, then An of P. What is the An of P here? First we can take D. Therefore, in the step 7, general particular solution Gn equals to 2. Therefore, here An of P, particular solution. The particular solution is denoted by An of P. Here An of P equals to some constant D. What I told to you, this D we have to substitute in the given equation. Okay, step by step I am explaining, my dear students. You can see here. You can see in the sixth step we calculated an of h. After that, what I told to you, this particular solution is an of d only here, an of d. So what I told to you in the step 8, substitution is sorry, this is step 7, am I right? This is step 7. Step 8, what I told to you, substitute an of p in the given non-homogeneous recurrence relation. Therefore, here a dn of p, this is the equation 5. This is the equation 5. Clearly observe. This is the equation 5. This equation substitute an of p equals to d. In that means substitute equation 5. This is the equation 5. In the equation, in the given non-homogeneous linear recurrence relation. This means equation 1. So equation 5 substitute in the equation 1. What is the equation 1? What they given in the equation 1? Check it. Here an minus 2 an minus 1 plus an minus 2 equals to 2. Okay, I am writing the equation 1 here. All of you listen. Equation 1 means an minus 2 into an minus 1 minus an minus 2 equals to 2. This is the given equation. Am I right? Yes or no? Student, this is plus. Am I right? Yes or no? You are not listening properly. Okay, substitute this an value in this equation. That means an equals to an of p equals to, what is the an of p? D. So an of n minus 1 is also p, because this is constant. An of n minus 2 is also d, because this is the constant. There is no n. Therefore, substitute d minus 2d plus d equals to 2. Finally, what happened? 2d minus 2d equals to 2. Finally, 0 equals to 2, which is wrong. So when we are getting wrong here, this is the very, very important, my dear students. I clearly told to you here, this is wrong. 0 is not equals to 2, but here finally we are getting 0 equals to 2. So if you getting 0 equals to 2, immediately you can come to here. What I told to you, the particular solution, first you can take d. Suppose it does not satisfy this condition, immediately you can take dn. Therefore, we can take dn now. So here we are getting wrong. Therefore, you can take the particular solution. That means the 8th step you can repeat. The same 8th step I am repeating. Substitute 5. Sorry, I am repeating here an of p equals to, clearly listen, my dear students. Here it is the very, very important what I told. First you can take d. Suppose d not satisfied, then you can take d into n. Then you can take d into n square. Then d into n cube. So here the first case is wrong. Here it is not satisfying. Okay. Now we can take an p equals to d into n. an p equals to, next one same, an p equals to d into n. Okay, here dn, here only d, here d into n. This is the equation 5. Once again same, substitute 5 in the given non-homogeneous linear recurrence relation 1. What is the non-homogeneous recurrence relation? An minus 2 into an minus 1 plus 2 into an minus 2 equals to 2. This is the equation from 1. This is the equation 1. In this equation 1, substitute this one. An of p means dn. An minus 1 of p means, at the place of n we have to substitute n minus 1. An of n minus 2 means at the place of n substitute n minus 2. Substitute these values here. An means dn. minus 2 into an minus 1 means d into n minus 1 plus is it 2n or only n?
Only an minus.
Only am I right? Check it. Yes or
Yes.
no? Yeah. Now what I told to you, the next one is d into what is it? An minus 2 n minus 2 equals to 2. Again simplify this one, dn minus 2dn minus into minus plus 2d plus dn minus 2d equals to 2. See here, dn 2dn minus 2dn plus 2d minus 2d equals to 2. Finally what happened? These two cancel, these two cancel. Finally what happened? 0 equals to 2. This is also wrong. Am I right? Yes or no? Are you understanding?
Yes,
Yeah.
sir.
Now, yes, now come to the third case. An of p equals to d into n square. Again same. This is the fifth step. That means substitute same. Substitute 5 in the equation in the given non-homogeneous linear recurrence relation 1. Second equation already you know. What is the second equation? An minus 2 an minus 1 plus 2 plus an minus 2 equals to 2. In this equation we have to substitute dn square. But what is dn square? Check it here. What is dn square? See, an equals to d into n square. An minus 1 means at the place of n we have to substitute n minus 1 square. And an minus 2 means d into n minus 2 whole square. So these three we have to substitute in the equation. See, first one is, what is the equation? An means d n square minus 2 into d into n minus 1 square plus an minus 2 means d into n minus 2 whole square equals to 2. Am I right? Yes or no? This is an minus 2 into an minus 1 plus an minus 2 equals to 2. Am I right? Yes or no? Are you listening? A plus b whole square formula. What is the a plus b? A plus according to a minus b whole square formula, how can we write? N square minus 2n plus 1 plus d into here, how can we write? N square plus 4 minus 4n plus 4. Am I right? Are you okay? Yes or no? Is it right or wrong? Is it right or wrong? No one responds. Yes. Next, 2 to the 4 d n minus 2d. I think it is plus, minus into minus plus. Am I right? Please respond. Check it. Is it right or wrong? Please check it. Okay. Any mistake is there?
No, sir.
Yes or no? 4 dn. Here the minus 4 dn. You can cancel directly. Directly can cancel. Plus 4 dn. These are minus 4 dn. Am I right? Check it. Right or wrong? Please check it. What are the steps I am writing? These are right or wrong? Please check it, my dear students. Plus 2d equals to 2. Okay, here also we can cancel these two terms. We can cancel these two terms. Then finally you will get 2d equals to 2. Is it right? Yes or no? Finally d equals to 1. Are you okay?
Yes.
Yeah, here finally we did here see in the second case we got wrong 0 equals to 2. Even in the first case also we got wrong 0 equals to 2. But here what happened? We got the constant d equals to 1. Therefore, an equals to, therefore particular solution an of p equals to d into n square. This is d into n square from equation 5. Here d value already you calculated the d value. Therefore, an of p equals to d value is 1 into n square. Finally, an of p equals to n square. This is our required particular solution. Are you clear? Yes or no? Are you understood? This is an of p. So after getting the an of p, what I told to you, you can check it here. See, after getting that, you will get the equation 6, that is the general solution, equation 6. But here initial conditions are there. Initial conditions are given here. Here initial condition, this is the equation 6. This is the equation 6. Equation 6. Initial conditions means see the problem they given a naught equals to 25, a1 equals to 16. A naught equals to 25 and a1 equals to 16 is called the initial condition. Keep this point here, this is called the initial condition. So a naught equals to 25. Keep this point, initial conditions. Now come to the point, initial conditions. This is the step number 8, 7 or 8. Just a minute. I will check it. What is this step? Step 4. Step 9. Yeah. Come to the point. This is the step 8. Now come to the step 9. Oh, sorry. Stepwise, I am telling everything to you. Okay. Now come to the step 9. What is this step 9 means? Initial conditions. Step 9. Initial conditions. Oh, sorry, 1 minute. Here we got the particular solution. This is the particular solution. We require the general solution. What is the general solution? Particular solution. This is the particular solution. General solution. Therefore, general solution. General solution. What is the general solution? I told to you. General solution of non-homogeneous recurrence, linear recurrence relation. What is the general solution? An equals to an of h plus an of p. Already they given an of h, already you calculated c1 plus c2 into n. This is the an of h plus an of p, already you calculated n square. This is the equation 7. This is the equation 7, my dear students. Now come to this is the general solution. Now initial conditions, what they given? Initial conditions, a naught equals to 25 and a1 equals to 16. Now take it general solution. General solution of 1 is an equals to c naught plus c1 into n. See here, c naught or c1. We use the c1, c2. C1, C2, the general solution C1 plus C2 into n plus particular solution already you calculated d into n square. This is the general solution. Here already just substitute n equals to 0. If you substitute n equals to 0 here, a naught equals to c1 plus c2 into 0 plus d into 0 square. Finally, what happened? A naught means 25 already they given. 25 equals to c1 plus 0 plus 0. Finally, you will get 25 equals to c1. See here we got the c1 value. Here we got the c1 value. Similarly, just come to the n equals to 1. If you substitute n equals to 1, what happened? A1 equals to c1 plus c2 into 1 plus d into 1 square. Finally, what happened? Finally, what can we find here? A1 equals to c1 plus a1 means already they given the a1 value. What is the a1 value? A1 is 16. 16 equals to c1. C1 value already you know, you calculated already. Already you calculated. This is the 25 into c1, c2 plus d. Therefore, this can be written as 16 minus 25 means minus 9 equals to c2 plus d. Here we got the c2 plus d. Are you okay? Are you okay, my dear students?
Sir, D equal to 1.
Yes, I am writing. Here, d equals to 1. Already you know that. Here you know that d equals to 1. D equals to 1 already you calculated. D equals to 1. Okay, but actually here no need to take d. See here, no need to take d here. Direct n square is there. Already we substituted. No need to take d here because d is 1. Am I right? Yes or no? Yes or no? Here d value is 1. Therefore, no need to take d. Am I right? Please respond. Therefore, finally C2 equals to minus 10. Am I right?
Yes, sir.
Yeah. Substitute the C1 and C2. Substitute. 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 C1 equals to C1 equals to 25, comma C2 equals to minus 10 in equation 7. Equation 7 means general solution. General solution. What is the general solution? An equals to C1. C1 means 25 minus C2. C2 means 10 into n plus n square. This is our final answer. Are you clear? Anyone have any doubt in these steps? Yes or no? It contains the many steps, but it is a very easy, my dear students. Are you okay? Are you okay? Yes or no? Have you understood
Yes, sir.
properly? Yeah, this is the first model. Okay, remaining two models are there. That two models we have to discuss. If you are able to listen, then I will continue the at least one of the model, next model. Otherwise, I will discuss in the class. That is our wish. Can I start in the class? Can I explain this one in the class or can I continue? Because here there are only 31 students. Here there are only 31 students. That's why I am asking. Can I discuss in the class?
Yes, sir.
Yes, sir.
Okay, Amma. Okay. I will share this PDF what I discussed in the today's class.
Okay.
Okay. If you need anything, I will take the one more class in the next Saturday. Because there are only 31 students out of 30 students out of more than 60. Am I right? Yes or no?
Sir.
Therefore, I will take the same class, one more class in the next Saturday because today only few students, 50% students only attended to this class. I will share this recorded video lecture also to you. Okay, who are absent, they can see this video, and I will send the today's PPT also. PPT means what I screen PDF of the whiteboard. Are you okay? Yeah, is there any doubt in this today's class? Dear students, please tell me any doubts.
No, sir.
Tell me, Amma.
Sir, when is the mid for DMS?
DMS next weekend.
Next week.
Yeah, weekend.
It'll be on the weekend.
Weekend means Friday.
Okay.
Friday we have a class. Friday afternoon, I think. Am I right?
Yes, sir.
Yeah, Friday afternoon, I will conduct the mid examination for DMS. You can check your WhatsApp. Already I shared the today's whiteboard, today's content, what I written on the screen. Completely step by step, I clearly explained. Already you can see. Have you got it?
Yes, sir.
Yes, sir.
Yeah, that is my dear student. Already each step I clearly explained. You can see each step and you can easily understand. Practice the remaining similar problems. Are you okay? Okay. I will close the session. If required, I will conduct the one more class in the coming Friday, coming Saturday, in the same day. Okay. Okay. Can I end the session?
Yes, sir.
Are you okay? Okay. Thank you.